Hello everyone, welcome to PW Gulf. So today we'll be doing the recap session of the chapter Motion of System of Particles and Center of Mass. We have done this chapter in our class and today we'll be revising the chapter. So let's see what topics we'll be covering today. We'll be studying system of particles and rigid body. What is a system of particles and what is a rigid body, okay? Then we'll be covering what is center of mass, okay, how we define center of mass, what center of mass tells us, why we study center of mass. Then we'll be going on center of mass of composite systems. First we'll be calculating how center of mass is calculated. Then we'll be studying it for the composite system, okay. First we'll study it for rigid bodies, then we'll study it for composite system. Then we'll study the motion of center of mass, okay. So let's start with very first thing. What is a system of particle? Particle is defined as an object whose mass is finite but size is very small, that it is almost negligible, okay. So any object whose mass is finite but whose size and internal structure can be neglected, okay. There is no specified size or structure of that particle, that we say point particle or point mass. Now next is system of particles. When many such particles come together and they form a structure or form a system, okay, they form some system in which there are two types of forces, internal and external forces, okay. The system is withheld, they withheld each other by applying some force, any interactive force they can apply, that is called a system, okay. So a collection of very large number of particles which mutually, okay, which mutually interact with each other. How particles can interact? They can interact by exerting forces, okay. They interact by exerting forces. When we have a many number of collection of particles which interact with each other by exerting some forces, they held the system with that forces, that is called a system of particles, okay. So whenever we have a system of particles, two types of forces are acting on the particle. One is internal and the one is external. Now what are internal forces? To keep the system as one, okay. So if we have a ball, the ball doesn't break into its constituent particles or atoms. The atoms are keeping each other by side by applying some force of attraction, okay. The atoms are at their position only because they are attracted to each other by forces. Such forces are called internal forces, okay. Such forces are called internal forces. The mutual forces exerted by the particles of a system on one another, okay. When we have one particle of a system which is exerting force on the other particle of system, that force is called internal force, okay. That force is called internal force. Now what are these forces responsible for? What change they will make? They will keep the system together, okay. They are responsible for holding the system as one unit, okay. If the atoms are not attracted to each other by internal forces, they will break off into its constituent particles. See, so the ball will not remain as a ball, it will break into atoms. So they are responsible for holding together the particles as a single object, okay. They are responsible for maintaining the shape and size of the system, okay, or structure or the object which they are a part of. Clear? So internal forces which are exerted by particle of a system on one another. One particle is attracting or it can repel also the other particle of the system. Now let us see external forces. The forces which are applied on the system by some other agency externally, okay. So whenever we have outside forces exerted on an object by external agent, someone outside from the system is exerting a force on the particle, these forces are called external forces. What change will external forces make? Okay, they are responsible for changing the state of the motion. Okay, they are responsible for changing the state of particle system, its state of motion, its state of rest, direction of motion. They are responsible for changing the state of the system. So this is internal and external force. We have a body whose shape and size is fixed, okay, and we have a body, when we apply some force, its shape changes. So which one is rigid and which is not rigid? Rigid is anything that will maintain its shape, okay, that is having a fixed shape. And we have another body, when we apply, it stretches. When we apply force like this, it compresses. It cannot maintain its state, okay, it cannot maintain its shape. So the one which cannot maintain its shape is not rigid. So what is a rigid? Rigid body is something or any object which maintain its shape and size, okay, which maintain its shape and size. It always has a fixed shape and fixed size. Under the action of forces, rigid body can translate or rotate, but it cannot change it. Under the action of forces, rigid body doesn't change its shape, okay, it maintains its shape. Such a body is called rigid body, okay. A rigid body is a body with perfectly definite and unchanging shape, okay. So it will have definite shape, okay, definite shape. Its shape will not change. Now suppose we have any arbitrary rigid body, okay, we have any arbitrary rigid body. There are two particles of this rigid body, M1 and M2. Rigid body can be thought of as made up of number of particles, okay. So rigid body is a system of particles. M1 and M2 are two particles of the system. If this distance between 1 and 2 changes with time, then what will happen? M2 will move forward, M1 will lag behind, or M1 will move forward, M2 will lag behind. If distance between two particles is changing, then body's shape will change, okay. If we have a circle, if this point is moving with 5 meter per second and this is moving with 2 meter per second, what will happen? In the same time, it will cover more distance, it will cover less distance. Our circle will get ellipsed, okay. Our circle will be compressed from the both sides and it will oblate structure will be made, okay. Its shape will change. So distance for a rigid body to maintain its shape, distance between the any two particles of the body should not change, okay. Distance between any two particles, distance between any two particles of the body, distance between any two particles of the body does not change with time, okay. It cannot change with time. So distance between any two particles of the body doesn't change with time, then it is called a rigid body, okay. The distance between all pairs of particles of a such body do not change. If it changes, then shape will change, okay. So what will happen? If we have a rigid body, distance between any two particles, okay, between them is constant with time, such a body is called rigid body. Now let us come to center of mass, okay. Let us come to center of mass. Suppose we have a hammer like this, okay. Now this is a M mass hammer. We have a hammer like this. We applied a force F on this hammer. How will the hammer move? Hammer will move forward in a straight line. Okay, we applied a force F, a hammer will move in a straight line like this. Okay, hammer will move in a straight line. Now suppose the hammer is like this. Okay, the hammer is like this, and we applied a force F over the handle. We applied a force F over the handle. What will happen if we apply a force F over here? See, if we apply a force F over here, it will rotate simultaneously, translate. Okay, due to force F, now I have holded this, then it is only rotating. If I didn't hold this pen and apply a force over here, what will happen? It will move forward as well as it will rotate. Okay, so after some time, okay, after some time, my hammer position will be like this. Okay, after some time my hammer's position will be like this, and then after some time it will be like this. Okay, so there is a point on this hammer. There is a point on this hammer which is behaving in a certain way. Okay, which is behaving in a certain way. Now if M is my mass of the hammer and I take a M mass point particle, okay, and I take a M mass point particle and I apply the same force F on this particle, how the particle will move? It will move in a straight line. If I have a point mass particle of M size and apply a same force and apply the same force F on this point particle, then it will move in a straight line. So there is a point on this rigid body. Okay, there is a point on this rigid body hammer which will move just like the way this point mass particle of the same mass as hammer is moving under the action of same force. Okay, there is a point on this rigid body which is moving in the same way. It is moving in the same way as this point mass particle of the same mass is moving under the same force. Then this point is called center of mass. Okay, then this point is called center of mass. So what is center of mass? Center of mass of a system of particle is that single point which moves in the same way in which a single particle having the total mass of the system, okay, which will move in the same way as a single particle having the total mass of the system will move when acted by the same external force. Okay, the center of mass of the body will move in the exactly same way as this point particle of the same mass will move under the action of the same external force. That point is called center of mass. Now see, if I concentrated whole of the mass of this body onto a point particle, that particle is moving in the same way as this point on the body center of mass is moving. So we can assume that, okay, we can assume that whole of the mass of the body is concentrated at its center of mass. Okay, so we suppose it, okay, we suppose it, center of mass, actual mass is distributed all over the body, but it is a hypothetical point where we assume that all the mass of the body is concentrated. Okay, because it behaves like such. Okay, under the action of force it behaves like such. So it is a whole mass of the body is supposed to be concentrated. This is very important. It is not actually concentrated. It is supposed to be concentrated for describing which type of motion is this? For describing its translatory motion, okay? For describing its translatory motion. It is a point. Now, center of mass is a point where whole mass is supposed to be concentrated, okay? Where whole mass is supposed to be concentrated. Next is, it will be a hypothetical point where whole mass is supposed to be concentrated. It describes the translatory motion, okay? It describes translatory motion, okay? It describes translatory motion of the body, okay? It describes translatory motion of the body. Now, center of mass can lie outside or inside the body, okay? Center of mass can lie outside the body or inside the body. It can lie outside the body or inside the body. Now, let us calculate how center of mass is calculated. First is for two particle system, okay? If we have two particles, in the x, y, z coordinate system whose position coordinates are m1 is x1, y1, z1 and m2 is having the coordinate x2, y2 and z2, okay? So we have two particles whose coordinates are x1, y1, z1 and m2 is having x2, y2, z2. The position coordinates of center of mass are. Now, what will be my coordinates of center of mass? X coordinate of center of mass will be equal to m1 into x1, mass of the particle into its x coordinate, then plus m2 into x2 divided by m1 plus m2, okay? How we define the x coordinate of center of mass? m1 into x1 plus m2 into x2 divided by m1 plus m2. Similarly, y coordinate of center of mass is m1 into y1 plus m2 into y2 divided by m1 plus m2. m1 plus m2, this is the y coordinate, and z coordinate will be m1 into z1 plus m2 into z2 divided by m1 plus m2. This will be my z coordinate of the center of mass. This is how we define x, y and z coordinate of center of mass, okay? m1 x1 plus m2 x2 divided by m1 plus m2, m1 y1 plus m2 y2 divided by m1 plus m2, m1 z1 plus m2 z2 divided by m1 plus m2. This will be our position coordinates of the center of mass, the point where whole mass is supposed to be concentrated. See next, if we have n particles, instead of 1 we have m1, m2, m3, mn up till so on n particles, okay? So my xcum, this will be m1 into x1 plus m2 into x2 m3 into x3 up till so on mn into xn divided by m1 plus m2 plus m3 up till so on mn, and similarly ycom. Okay, now how can we write it in this? Can I write it in this summation form, that summation I goes from 1 to n mi into xi divided by summation I goes from 1 to n summation mi? Can we write it like this? So this is our xcom. Okay, this is our xcom. Similarly ycom will be summation I goes from 1 to n mi into yi divided by summation I goes from 1 to n mi. Okay, this is my y coordinate of the center of mass, and similarly we can write the z coordinate of center of mass, summation I goes from 1 to n mi into zi divided by summation I goes from 1 to n mi. Okay, this will be our z coordinate of the center of mass. So if we have n particle system, we can define the coordinates of center of mass like this. Position vector form. Now if we have x, y and z coordinate system, now see, if we have x, y and z coordinate system, and we have a particle of mass m1 over here and m2 over here. Okay, we have a particle of mass m1 over here and m2 over here. So these are my coordinates. This is my position coordinates of the center of mass. Sorry, position coordinates of m1 and m2. r1 is the position vector, this is origin. r1 will be the position vector of m1. Similarly r2 is my position vector of m2. Now if we have to find the position vector of center of mass, okay, position vector of center of mass will be, what will be position vector of center of mass? So RCOM will be given by m1 into r1, mass of 1 into position vector of 1, plus m2 into r2 divided by m1 plus m2. This will be my position vector of the center of mass. Okay, this is my position vector of center of mass. Suppose if we have n particles, for n particles, what will be my RCOM? RCOM will be summation I goes from 1 to n mi into ri divided by summation I goes from 1 to n summation mi. Okay, this is my position. So if let us suppose that center of mass is at this point, okay, let us suppose that center of mass is at this point, then this is the position vector of center of mass. Okay, this is RCOM. This will be the position vector of center of mass. Okay, this is how we define center of mass in my position vector form. Now let us move ahead. If we have a center of mass in continuous mass system, till now we were having discrete mass systems. Okay, till now we were having discrete masses. some point particles m1, m2, m3, they were present at some coordinates. Okay, mass was discrete. Now if we have a continuous mass system like this, see this stylus is having mass at every point. Okay, every point it is having mass. We have a continuous distribution of mass. So in discrete system, xcum is equal to summation mixi divided by summation mi. Is it so? Okay, it is summation mixi divided by summation mi. Now if we have a continuous mass distribution, what we can do is, like if we have a rod and there is mass at every point on this rod, so what we did is we divided this rod into very infinitely small, okay, into infinitely small masses dm. Okay, we can calculate infinitely, we can divide this rod into infinitely small masses dm. Now we can calculate the center of mass. Okay, position of this, if we take this as origin, we can calculate the position of this element dm. Okay, some other element will be at different distance, so it will be dm into x1 plus dm into x2 plus dm into x3 plus dm into summation of all the dm into their respective coordinates. Okay, summation of product of all the dms and their respective coordinates. This is mi into xi. Now when we have infinite sum, we can write it in the form of integration. Okay, we can write it in form of integration. So for continuous mass system, this summation mixi will become mass is dm, its position is x, and the summation will turn into integration. And summation of all the mi will be summation of dm. This is my xcum. Okay, in continuous mass system, we will have x coordinate of center of mass like this. Okay, x coordinate of center of mass like this. Now summation of dm will give my total mass, summation of dm will give my total mass of the body, so we can write it summation of x dm also. Okay, we can write it in this form as well. Okay, similarly ycum will be summation of dm into y divided by summation of dm, and similarly zcum will be summation of dm into z. Sorry, not summation, integration. Really sorry, not summation, integration. Integration of dm into y divided by integration of dm. zcum will be integration of dm into z divided by dm. Okay, this will be my ycum and this will be my zcum. Okay, we can also write it like this: 1 by m into integration dm into y, and we can also write it like this: 1 by m into integration dm into z. Okay, integration of dm will give me the whole mass of the body. This is my ycum and this is my z coordinate of the center of mass. Okay, so let us calculate it. Let us calculate it for one body like rod. Okay, let us calculate it for rod. Okay, we have a rod of length. Rod is having mass L and length L. Okay, mass M and length L. Let us take this coordinate at 0. So coordinate of this point will be L. Okay, coordinate of this point will be L. Now we will take a small mass element dm. Okay, we will take a small mass element dm on this rod. This dm is having some width dx. Okay, this dm is having some width dx and its position from the origin is x. Position from the origin is x. Now let us calculate the mass dm first. Okay, mass per unit length. Mass per unit length of rod. This will be equal to lambda will be m by L, mass per unit length. So unit length is having the mass m by L. Therefore we can write dm will be equal to lambda into dx. Yes, mass per unit length, mass density, linear mass density, mass per unit length is having m by L. Okay, m by L is the mass in unit length. If unit length is having this much mass, how much mass will be dx? Dx length have, dx will have lambda into dx mass. Okay, so dm will be lambda dx. So from here we will get dm is equal to m by L into dx. Okay, it will be m by L into dx. Now let us calculate xcum. xcum will be integration of dm into x divided by integration of dm. Now calculate it. Put the value of dm. Value of dm will be m by L into dx and x as it is divided by integration of dm m by L into dx. Now tell me one thing, what will be limit of x? X can be, if we consider element over here, x is 0. If we consider element over here, x will be L. So limit of x will go from 0 to L. Limit of x will go from 0 to L. Now this m by L will come out. We will have xcum will be m by L into integration of x dx from 0 to L and m by L into integration of dx from 0 to L. M by L gets cancelled. xcum will be integration of L. It will be x square by 2. Limit 0 to L. Integration of dx is x. Limit 0 to L. Substituting the limits, we will get L square by 2 divided by L. So our x center of mass will be 1 by L into L square by 2. 1 L and L gets cancelled. So for a uniform rod, center of mass is at L by 2. Okay, for a uniform rod, center of mass is at L by 2. This is how we calculate center of mass in discrete continuous mass systems. Okay, this is a uniform rod. Okay, so for uniform rod, center of mass is at a distance L by 2, that is half of its length. Okay, for continuous we will write it in the form of integration. How we solve it? Consider a mass element dm having some length. If it is a disk, it will have some area. If it is a sphere, it will have some volume. Okay, then calculate dm and then we can calculate the center of mass coordinate. Okay, now let us come to center of mass of some rigid, uniform rigid bodies. So see, center of mass of uniform bodies L by 2. For a rod it is at L by 2. For uniform rigid bodies or regular shaped bodies, okay, for regular shaped bodies having uniform mass density, center of mass will coincide with the geometric center. Okay, it will coincide with the geometric center. So what we have is, for ring, center of mass will be at its center only. Okay, center of mass will be at its center only. Same goes for the disc. Center of mass will be at my center of the disc only. For triangle, center of mass is at the centroid. Okay, what is the center of triangle? Centroid. So center of mass is at centroid. For square, it will be at the point where the diagonals meet. If we have a square of side A, it will be at A by 2, A by 2. Then if we have rectangle, okay, if we have rectangle, for rectangle it will be having same diagonals where the point where diagonals meet. This will be our center of mass at L by 2 and B by 2, length and breadth. L and B. If we have a hollow cylinder or a solid cylinder, okay, we have a hollow cylinder or a solid cylinder, any type of cylinder we can have, of height h, okay, h is my height of the cylinder, then center of mass is at height h by 2, exactly in between the center, okay, exactly in between the center of the cylinder, h by 2. Next is hollow cone. For hollow cone, center of mass is at a distance h by 3 from the base, okay. For a right circular hollow cone, center of mass is at h by 3. For a solid right circular cone, center of mass is at h by 4 from the base, okay, h by 4 from the base. If we have a rod of length L, center of mass is at half L by 2. If we have a semicircular ring, okay, if we have a semicircular ring, then center of mass is at a distance 2r by pi from the center, okay, center of mass is at a distance 2r by pi from the center. For a semicircular disc, okay, for a semicircular disc, it is at a height 4r by 3 pi from the center. If we have a hollow or solid sphere, okay, if we have a hollow or solid sphere, center of mass will be at its geometric center only, okay. Next, if we have hemispherical shell, okay, hollow hemisphere, okay, hollow hemisphere, then center of mass is at a height r by 2 from the center, okay, it is at a height r by 2 from the center. If we have solid hemisphere, it is at a height 3r by 8 from the center. This is the center of mass of some uniform, regular, rigid bodies. You have to memorize all these center of mass coordinates. Now let us come to center of mass of composite systems. That is when a system is made up of more than one rigid bodies, okay, it is made up of more than one rigid bodies. So how to find its center of mass? Suppose we have four rings, okay, suppose we have four rings, each of mass, we have four rings, each of mass m and radius r, okay, we have four rings, each of mass m and radius r. Let us consider this as my origin, okay, let us consider this as my origin. Now calculate the center of mass of all the rings. Calculate the position coordinates of center of mass of all the rings. This will be C1, C2, C3 and C4. Now what is C1? 0, 0. What is C2? If R is this radius and R is this radius, it will be at 2r comma 0. Where will be C3? It will be 2r comma 2r, and where is C4? It will be 0 comma 2r. These are my coordinates of center of mass of the respective rings. Now center of mass is a point where we assume that whole of the mass is concentrated. So we can assume that whole of the mass of this ring is present at C1, whole of the mass of this ring is present at C2, similarly C3 and similarly C4. Whole of the mass is present at this, then it will become a discrete system, and then it will become a discrete system. So position coordinate XCOM, this will be equal to m1 into x1 plus m2 into x2 plus m3 into x3 plus m4 into x4 divided by m1 plus m2 plus m3 plus m4. This is how we can find the center of mass of composite systems. So XCOM will be mass of the first ring is m, into it coordinate 0. Okay, mass of second ring is m into its position coordinate 2r, third ring m into 2r, and fourth ring m into 0 divided by m plus m plus m plus m. So what it will become? XCOM will become 2mr plus 2mr, 4mr divided by 4m and 4m gets cancelled. So XCOM will be r. Okay, position coordinate of center of mass is r. X coordinate of center of mass is r. Similarly, if we calculate the YCOM, it will be m into 0 plus m into 0 plus m into 2r plus m into 2r divided by 4m. So YCOM will also come out to be 4mr divided by 4m. 4m and 4m cancel out. Y center of mass will be r. Okay, YCOM will be r. Now see, center of mass is at r distance this side, r distance this side. Okay, this is point where center of mass of the whole system will lie. Okay, so for additive composite systems, what we have is treat each body center of mass as if whole of the mass is present over there. Then we can convert it into discrete system and then we can calculate it. Okay, so treat each body as a point particle present over the center of mass. Okay, treat each rigid body as a point mass particle present over the center of mass. So this is how we calculate the center of mass for composite systems. Now let us see center of mass for composite subtractive systems. Okay, for subtractive systems. Now let us see it for subtractive systems. If we have a disk, okay, we had a disk of mass m and radius r. We had a disk of mass m and radius r. From this disk, okay, from this disk we removed from this disk we removed another disk. Okay, from this disk we removed another disk whose diameter is r. So radius of this disk will be r by 2. From this disk we removed this disk. Okay, this disk is removed. Okay, this is a disk. We had a disk of mass m and radius r. From this disk we removed some other disk having some mass, okay, whose radius is r by 2. Now tell me one thing, we can treat the removed mass as negative mass. Okay, in additive systems we had two bodies. Okay, then we added their respective, then we calculated their respective center of masses, and we have an additive system. Two rings are present. Calculate their respective center of mass. Apply the formula of m1 x1 plus m2 x2. Now if we have a complete disk, okay, we remove some portion from this disk, we will get this. Okay, we will get this. So if we take this center of mass, this will be this center of mass of the removed portion. Okay, Take removed mass is negative, we will get the remaining. Okay, we will get the remaining. So we will treat the removed mass as negative mass. Okay, take removed mass as negative mass. Okay, take removed mass as negative mass. So what will be our XCOM? XCOM will now become m1 into x1 minus m2 into x2 divided by m1 minus m2. This is how now it will look. Okay, this is how now it will look, because we had a complete disk of mass m and radius r. From this a small portion, okay, from this a small disk of radius r by 2 and some mass m prime is removed, so that we get this. Now we have to find the center of mass of this. So treat negative mass, the removed mass. Now see, let us calculate the mass which is removed. Mass per unit area of disk. Mass per unit area of disk. This will be equal to, sigma will be equal to m by pi r square. M mass is distributed all over the radius r, so mass per unit area will be m by pi r square. So we can calculate this mass. Okay, we can calculate this mass. So unit area is having m by pi r square. How much mass will by this area r by 2? How much mass my disk having r by 2 radius will have? So m prime will be equal to m by pi r square mass per unit area into the area removed, m into r by 2 whole square. Okay, this will become m by pi r square into pi r square by 4. Pi r square cancel. We will get m prime is equal to m by 4. Okay, we will get m prime is equal to m by 4. Mass per unit area is m by pi r square. So unit area is having the mass m by pi r square. So pi into r by 2 square will have the mass m by pi r square into this area. Okay, this is how we can calculate the removed mass. Now calculate XCOM. Calculate XCOM. Take this as origin. Let us take this as origin. So x1 will be 0, x2 will be, this distance will be r by 2. So x2 will be r by 2. Okay, x2 will be r by 2. Now calculate XCOM. It will be mass of disk is m into m1 x1 minus m2 x2 divided by m1 minus m2. So XCOM will be m1 is m into 0 minus m2 is m by 4 into its coordinate is r by 2 divided by m minus m by 4. So XCOM will be minus m by 4 into r by 2 divided by m minus m by 4. This will be 3m by 4. Now this m by 4 gets cancelled. So from here we will get that XCOM is equal to minus r by 6. Okay, XCOM will be equal to minus r by 6. This is the position coordinate of center of mass. Okay, this is the position coordinate of center of mass. So because it is coming in negative, we have taken this as origin. So it will shift to this side. Okay, now center of mass will be here at a distance minus r by 6. Okay, this distance will be minus r by 6. Clear? Center of mass will always lie towards the heavier side, so it will be minus r by 6. Clear? This is how we calculate center of mass in subtractive systems. Okay, if we have for uniform mass distribution, for uniform mass distribution we can also write it in the form of area and volumes. So XCOM will be equal to M1 into A1 minus M2 into A2 divided by M1 plus M2, and in volume, for area, for volume distribution we will have M1 into V1 minus M2 into V2, it will be A1 into X1 minus A2 into X2 divided by A1 minus A2. It will be V1 into X1 minus V2 into X2 divided by V1 minus V2. We will take A2 and V2 are the removed area or volume. Okay, A1 and A2 and V2 are the removed area and volume. If we have a rigid body of uniform mass density and some area is removed, just like in this disk case, okay, this area is removed, we can write mass will be equal to area into we can write mass as density into area. Okay, see, mass per unit area, that mass density into area. Similarly, M2 will be mass density into area. So this density will come out as common and it will get cancelled. We will be left with A1 X1 minus A2 X2 divided by A1 and A2. As we treated removed mass as negative, removed area and volume will be also treated as negative. Okay, it just in this formula, how we get this? How we get this? This can be calculated like this. M1 will be sigma into A1. Okay, M2 will be sigma into A2 divided by sigma A1 minus sigma A2. So sigma will get cancelled. We will be left with A1 X1 minus A2 X2 divided by A1 minus A2. Okay, this is how we got this formula. For if we have area density, like mass is distributed over sheet, surface, disc, all such surfaces, lamina, square plate, rectangular plate, then we will use area. If it is sphere, volume. Okay, if we have a sphere, and then we will use the volume one. Okay, this is how we calculate center of mass of composite systems. Now let us come to motion of center of mass. Okay, now we know that RCOM is given by M1 R1 plus M2 R2 up till so on Mn Rn divided by M1 plus M2 plus Mn. Okay, now take M is equal to M1 plus M2 plus Mn, mass of the whole system. Okay, if we have mass of the whole system, capital M is equal to M1 plus M2 up till so on Mn. Now differentiate this equation. What this, take this to this side, we will get M into RCOM is equal to M1 R1 plus M2 R2 up till so on Mn into Rn. Differentiate this equation on both sides with respect to time. Differentiate on both sides with respect to time. Okay, differentiate on both sides with respect to time. M is constant, we will get drcom by dt. Rate of change of position coordinate of center of mass is equal to m1 into dr1 by dt plus m2 into dr2 by dt up till so on mn into drn by dt. This is what we will get. Now, rate of change of position, if all the system particles are moving, okay, if we have a system of particles and all particles are moving with some velocity v1, v2, vn up till so on, then dr1 by dt is representing velocity of first particle, dr2 by dt is representing velocity of second particle. And similarly, if all the particles are moving, center of mass will also move with the body. It will not be present over there only. So drcum by dt will give us rate of change of position coordinate of center of mass. Okay, position vector of center of mass is changing at a rate drcum by dt. So this is the velocity of center of mass. Okay, we will get m into vcom is equal to m1 v1 plus m2 v2 up till so on mn into vn. Okay, this is what we will get. Okay, name this as equation number 1 and name this as equation number 2. Okay, so from here we will get that velocity of center of mass is equal to m1 v1 plus m2 v2 up till so on mn vn divided by m1 plus m2 up till so on mn. This will be my velocity of center of mass. Okay, this is velocity of center of mass. Now if we differentiate 2 with respect to time, if we differentiate equation number 2 with respect to time, we will get m into rate of change of vcom by dt is equal to m1 into dv1 by dt plus m2 into dv2 by dt up till so on mn into dvn by dt. Now what are all these? This is m into acom, acceleration of center of mass, is equal to m1a1 plus m2a2 up till so on plus mn an. This will be our equation number 3. This will be our equation number 3. So from here we will get that acceleration of center of mass is equal to m1a1 plus m2a2 up till so on mn an divided by m1 plus m2 up till so on m. This will be my acceleration of the center of mass. Okay, this is our acceleration of center of mass. Now see, from equation number 3 we can write it as, from equation number 3 we can write it as mcom is equal to net force on F1. M1A1 will give me net force on 1. Yes, mass of one particle into its acceleration. It is net force on 1 plus net force on 2 up till so on plus net force on nth particle. Now some forces are internal, some forces are external. So total force on one particle will be internal force plus external force on particle number 1. Then similarly, net force on particle number 2 will be internal force plus external force on particle 2 up till so on internal force plus external force on particle number n. So we can write this as internal force on 1 plus internal on 2 plus internal on 3 and so on. So we can write it as internal force on 1 plus internal force on 2 plus internal force on nth particle, and similarly external force on 1 plus external force on 2 plus external force on nth particle. This is how we can write this equation. Now we know that all the internal forces sum up to 0. Okay, all the internal forces will sum up to 0. If a particle, you have two particles, this will exert, then this will also exert. When we calculate it for whole system, F1 internal plus F2 internal will get cancelled. Okay, internal forces of all particles of whole system, sum of all the internal forces will be 0. So we will get that M into ACOM is equal to external force on 1, external force on 2 up till so on external force on nth particle. So we can calculate, or sum of all the external forces will give us net external force on the system. Okay, so M into ACOM, this will give me F net external, okay, or net external force. This will give me net external force on the system. So see, this is an equation which describes that center of mass will behave such that all the external forces are acting on the center of mass. Okay, center of mass will behave as if whole mass is present at the center of mass and all the forces acting on the system are acting on that point mass particle only. It will have such an acceleration. Okay, so this is how we describe the motion of center of mass. Now let us calculate the linear momentum for a system of particles. So if we have a system of particles having masses m2, m1, m2 up till mn, having velocities v1, v2 up till vn, then what we will have? Total linear momentum of the system. Total linear momentum of the system will be, what will be a total linear momentum of the system? So total linear momentum of the system will be my vector sum of linear momentum of respective particles. Okay, total linear momentum of the system will be my vector sum of linear momentum of respective particles. So total, what will be P1? M1 is having the velocity v1, M2 is having the velocity v2, so it will be Mn will have the velocity Vn. Okay, this will be my linear momentum of the system. Now if this is my linear momentum of the system, remember we have seen this equation somewhere, that m1 v1 plus m2 v2 plus up till so on mn vn is equal to m into vcom. Yes, so this is equal to P vector is equal to capital M into VCOM. Okay, capital M is equal to capital P. Total linear momentum of the system is equal to mass into velocity of center of mass. So system will have a momentum, total momentum equal to momentum of the center of mass. Okay, this will be equal to mass into velocity of center of mass, that is momentum of center of mass. Okay, this will be equal to momentum of center of mass. See, center of mass will give us the momentum of the whole system. Center of mass acceleration will give us the net force acting on the whole system. This is how center of mass describes a translatory motion. Now if we differentiate this equation, what we will get? We will get dp by dt is equal to m into dvcom by dt. So from here we will get that dp by dt is equal to mass into acum, and that is equal to net external force on the system. Okay, so rate of change of linear momentum of the center of mass gives us the net external force acting on the system. So this is how center of mass describes the translatory motion of the system. So this is all about the chapter center motion of center of mass and system of particles. So I hope you enjoyed this session and it was a quick revision session for you all. So thank you very much. Take care, keep studying, keep rocking. Goodbye.